Hello, everyone. Welcome to our webinar today. We are excited to have you. Today, we're gonna talk about the importance of intrinsic viscosity measurements presented by me and my colleague, Dr. Ochoa. So let's go ahead and get started. Before that, I will start with some quick background about the theory of intrinsic viscosity and the relevant equations. I will continue with a review of our VROC technology and a quick review of the specifications of MVROC2, our newest viscometer. Then I will share some intrinsic viscosity data that I've collected for polyethylene oxide with MVROC2. Then my colleague Christian will review the technology and the features of Initium 1+. And last but not least, he will present intrinsic viscosity data for sodium caseinate and guar-gum systems that he has measured with Initium 1+. So I would like to start off with going over the applications of intrinsic viscosity in a protein system. So you will understand why intrinsic viscosity is important and what we can learn from intrinsic viscosity measurements. Intrinsic viscosity is a crucial parameter that helps us determine the hydrodynamic radius of a protein as it moves through a solution under the influence of the Brownian motion. So it's a measure of the protein's overall size and shape in the solution. Intrinsic viscosity measurements also help us understand the protein-protein and protein-media interactions, which affect stability and shelf life of the protein formulation. This can be described by the Huygens constant and/or Kramer constant. We also can predict the viscosity of our solution at different concentrations using the intrinsic viscosity measurements. So one way to do this is to utilize the Ross-Minton equation to estimate the viscosity of a solution for a given concentration. In addition, from Stokes-Einstein relationship, we can determine the diffusion coefficient by knowing the hydrodynamic radius and intrinsic viscosity of the solution. Last but not least, you can calculate molecular weight of your system, polymer or protein, from the intrinsic viscosity using the Mark-Howink relationship and knowing the relevant constants. So we will go into further details on some of these topics in the next couple of slides. Okay, so let's see what we can extract from dilute solution viscometry. So we are going to talk about the theory behind it first, so you can understand what you are learning about your sample by doing these measurements and applying the theory to extract some other parameters and extract more information about your system. So one of the parameters that you can extract from the dilute solution viscometry measurements is intrinsic viscosity. So we want to make it clear what this parameter means and what it is telling you about your system. So if you think about viscosity as a function of concentration and first thinking about very low concentration limit, I mean concentration going to zero, very dilute system. What we know is that at this level, the molecules are very far or separated from each other, and they are not really interacting with each other. In this region or in this dilute regime, the viscosity reflects the individual molecule size or shape because there is no interaction between molecules. This viscosity refers to intrinsic viscosity, which is used to characterize the individual molecules. But as we increase concentration, please keep in mind that we still are in the dilute regime. the molecular spacing is going to decrease due to the fact that there are now many more molecules in the system. Now neighboring molecules can interact with each other, and pair interaction is going to become important and relevant, and it's going to increase the viscosity of the system. So now if we look at this plot of viscosity versus concentration, we see that at very dilute regime, say something up to 20 mg per ml, the plot appears to be linear. But at some point, you start seeing deviation from linearity. So that's the introduction of those pair interactions in the system that causes this deviation from linearity. Okay, well, let's look at, okay, yeah. Let's look at some relevant equations and the theory behind the intrinsic viscosity. I think this helps understand what the parameters mean and what they do. As we increase concentration, and as a result, we increase the viscosity of the system, right? So we are adding complexity to the system. The way we do mathematically, so we add this complexity to our equations is by adding higher order terms to our equation, which is going to introduce this complexity. So if you look at the equations here for the relative viscosity, so I mean the viscosity divided by the solvent viscosity. So the first term is a zero order term, which means that there is nothing in the solution and we only have solvent. And then we introduce first order term, which is linear in concentration, C. So we also can express this relative viscosity in terms of effective hot sphere volume fraction, phi. So later on you will see why we presented these two equations together. So the coefficient in the first order term is intrinsic viscosity, which tells you something about individual molecules and its characteristics. If you remember, at very low concentrations or dilute regime, the molecules are far separated and they are not interacting with each other. So the first order term is gonna tell you something about individual molecules, and it's going to depend on the molecular weight and the intramolecular interactions, and also it is dependent on the impact of solvent or solution medium. So now if we increase the concentration of the solution, mathematically we are going to introduce the second order term to the equation. This term is proportional to the square of the concentration. So at this concentration, since many more molecules are present in the system, they see each other, and so they are going to interact with each other. So the coefficient here in the second order term is going to tell you something about pair interactions in the system and how molecules are actually interacting with each other. So typically molecules can interact in two main ways. First, hydrodynamic interactions that refer to the effects of fluid flow on nearby molecules. Since we measure the viscosity by introducing a flow field, so these interactions arise because the movement of one molecule affects the flow field around it, which in turn influences the motion of nearby molecules. And the second way of interaction is thermodynamic interactions that can be repulsive or attractive. So some common examples of this type of interaction is electrostatic forces that arise from the interaction between charged molecules and van der Waals forces. So thermodynamic forces can also be modified by solvent composition and I mean changing the quality of the solvent, like changing the pH of the solution or ionic strength. So with that in mind, now let's go over the general process that we should follow for designing the experiments and having a successful intrinsic viscosity measurements. As I mentioned earlier, the first thing is to measure the viscosity of dilute concentration series plus the viscosity of solvent or the buffer, because we use the viscosity of the solvent to calculate the relative viscosity. So what we are going to have is the viscosity versus concentration plot in the dilute regime. So this technique can be used to analyze proteins, synthetic polymers, colloids, or self-assembled polymers and micelles. So there is no specific rule for the concentration range that you follow to make actually your concentration series. Based on that, it's going to be very dependent on your system and its components. It's going to be different between polymers and proteins and other systems. However, a general rule that can be used is that the relative viscosity minus 1 that is equal to intrinsic viscosity times concentration should be less than 0.2 or even higher, something around 0.3 or 0.4 still should be fine based on our experience in measuring intrinsic viscosity. So for polymer system, this product, I mean intrinsic viscosity times concentration, is called coil overlap parameter. So if you are dealing with a polymer system, you don't want to be in the position that the coils are interacting or overlapping with each other. It can happen if you increase the concentration of your system and get to the overlap concentration. So in that situation, the coils might experience some sort of interactions. So you still want to maintain these coils separate as the individual coils, that they do not interact with each other. Okay, so with that in mind, our goal is to extract intrinsic viscosity parameter from this type of measurements. But intrinsic viscosity is not only a number. By doing further analysis, you can extract more information about your fluid system. For example, we can relate intrinsic viscosity to a parameter that is called hydrodynamic radius. If you remember earlier on, I started talking about intrinsic viscosity by showing you these two expressions. I mean the relative viscosity in terms of concentration in the first equation and relative viscosity in terms of effective hard sphere volume fraction in the second equation. So if you take these two expressions, the first order terms are going to be equal here. So then if we re-express and rearrange the effective volume fraction in terms of concentration, Avogadro's number, molecular weight, and hydrodynamic volume, we can get the expression for hydrodynamic radius as a function of intrinsic viscosity and molecular weight, because hydrodynamic volume is related to hydrodynamic radius. So if you measure the intrinsic viscosity and if you know the molecular weight of your system, you can simply estimate hydrodynamic radius. One technique that is commonly used for measuring hydrodynamic radius is dynamic light scattering. So if you have an estimation of the hydrodynamic radius from DLS measurements or dynamic light scattering, and also intrinsic viscosity from viscosity measurements, then you can use this expression to estimate the molecular weight of your system. So these techniques, I mean viscosity measurements and DLS measurements, can serve as complementary techniques to each other. So there is one more equation that I want to go over before going over the VROC technology and sharing some data with you. This equation is called Mark-Hawving-Sakurada that relates the intrinsic viscosity of a polymer solution to its molecular weight and structure. So if we take the equation that we just had in the previous slide and we rearrange that equation, now we have the intrinsic viscosity that is proportional to the radius cubed divided by molecular weight. So in general, the intrinsic viscosity will be proportional to the molecular weight to some power. So both the prefactor K and the exponent A will depend on the solvent polymer system and solvent quality. Also, it depends on the temperature and the molecular weight range. So if you are dealing with a unique system, for example, if you do synthesis, then what you could do is to generate intrinsic viscosity versus molecular weight calibration curve and use that as reference for any new polymer sample you test. As you generate this calibration curve, you can estimate the molecular weight for your unknown sample by using the intrinsic viscosity measurements. But if you are dealing with common polymeric systems, then you can find the relevant constants, I mean K and A. You can find these parameters in the literature or polymer handbook, and then you can estimate or extract the molecular weight based on viscosity measurements. Actually, this equation helps you get more specific information about your system from the viscosity measurements. So with that in mind, I want to talk to you a little bit about the core of our technology so you will understand how it works and how it measures viscosity. Our technology is called VROC technology, or viscometer rheometer on a chip. It's basically a combination of microfluidics and MEMS. MEMS stands for microelectromechanical system. So we have a rectangular microfluidic channel where we have 4 pressure sensors which are linearly aligned across the channel. So we control the flow rate through the chip and monitor pressure drop as the fluid flows across the channel. So since we have a well-defined geometry and we know the widths and depths of the channel, we can calculate shear rate from the flow rate and the geometry of the channel. And knowing the dimensions of the channel and pressure drop, then we can calculate shear stress. And as you know, viscosity is shear stress divided by shear rate. So we have shear stress and shear rate. So we can get viscosity by this equation, shear stress divided by shear rate. So what we do is to control shear rate, measure shear stress, and then calculate viscosity. So after all of that, now let's look at some intrinsic viscosity data that we got with our MVROC 2. Later on, my colleague Christian will share more data that he collected with Initium 1+. So we have talked in the past and in our previous webinars about the advanced features of the MVROC 2, and we discussed the importance of those features. Today, I don't want to go over all the details, but just wanted to highlight that with MVROC2, you can get high quality and high repeatable data, which is a key in the intrinsic viscosity measurements. High repeatability is crucial in intrinsic viscosity measurements. So here I'm sharing some data I've collected for polyethylene oxide, PEO. I measured PEO at 5 different concentrations in the dilute regime, as well as the viscosity of the solvent, which was water in this case. So as I mentioned earlier, we need the viscosity of the solvent to calculate relative viscosity. So to perform the intrinsic viscosity analysis, the data must be rescaled appropriately. So the relevant equations are presented here to clarify the data rescaling procedure and the meaning of the extracted parameters. The two most common models that are used to analyze intrinsic viscosity are called Huggins and Kramer models. Basically, in the Huggins model, we plot reduced viscosity, which is the relative viscosity minus 1 divided by concentration. So we are plotting reduced viscosity versus concentration. And since we did rescaling to create this reduced viscosity, now we can fit a linear function to our data. So if you look at these red data points in the graph, the intercept then is going to give you the intrinsic viscosity, and the slope includes the KH, or Huggins constant, that quantifies the interaction between neighboring molecules. We calculated Huggins constant for our system by using the slope of this linear fit. This calculation gives us the KH of 0.37, which aligns with the value reported in the literature. By using this analysis, you see that the extraction of these parameters is easy. Kramer model is another method that is used for estimating intrinsic viscosity. This time, we plot inherent viscosity, which is the natural logarithm of the ratio of the viscosity to the viscosity of the solvent divided by concentration. So we plot inherent viscosity versus concentration, and here on the graph, it's shown by these blue data points. So like the Huggins model, the intercept is going to give you intrinsic viscosity, and the slope is going to give you the Kramer constant. And I also summarizes all these parameters I got for PO in this table. So if you compare the results from Huggins to Kramer, you see that the intrinsic viscosity extracted from these two models are close. That indicates the accuracy of our measurements and calculations. I also did further analysis and used the intrinsic viscosity to extract more information about this polymeric system. So I used Mark-Howing equation and the parameters that I found for PEO in the polymer handbook, and then I calculated the molecular weight of the PEO. The PEO I used for these experiments is sourced from Sigma Aldrich, and it has the molecular weight of 100,000. So you see how accurate our calculations are. The molecular weight calculated from Kramer is about 96K, and from Huggins is about 98K. So, and the calculated molecular weight matches perfectly with the reported value by the manufacturer. Now that we know the molecular weight and the intrinsic viscosity, we can estimate what hydrodynamic radius would be. Here is the hydrodynamic radius calculated from Huggins and Kramer models. So the literature also supports these values, and the PEO in this molecular weight range has this value of intrinsic viscosity and hydrodynamic radius. So, okay, after this quick review of intrinsic viscosity, now I'm gonna turn it over to my colleague Christian, and he's gonna review Initium 1+ and share some more data with you.
Thank you, Soha. So the Initium 1+ is our fully automated small sample viscometer. And this instrument can be used for automatically running all of your samples for intrinsic viscosity analysis. So the minimum sample volume that you need for this instrument is 19 microliters. And the minimum sample volume that you need to get your intrinsic viscosity data would be 50 microliters. So with this volume, you can get unlimited data, because after the syringe runs out of sample, that sample that was previously pushed out is simply retrieved back into the syringe. So this means that with just one sample, you can set multiple temperature, multiple shear rate conditions if you want. Once you load your samples and cleaning solvents, you can select the protocol and hit run, and all of the sample loading, measurements, and cleaning will be performed automatically for you. So with our latest updated software, this will be version 2.5.1. This will have updated cleaning protocols, and you will be able to run up to 4 samples in 1 hour. So this contrasts with a little over half an hour previously. Other than intrinsic viscosity measurements, you can also get a wide range of shear rate sweeps for your samples. So you can run up to 300,000 N per seconds with Initium. And this will allow you to do such things like performing adequate injectability analysis for your samples, and obtaining your antibody or protein cluster size by calculating a quantity called the Peclet number. And you can do all of this with the Initium as well as with the MBROC2. So this here is sodium caseinate protein. So this is used in dilute solute concentrations to change the texture of foods like coffee, creamer, cheese, and even ice cream. So this is derived from casein, which is the main protein that is found in milk. And in solution, it's going to self-assemble into these aggregates or micelles in solution. So understanding the size of these micelles is important because they affect the rheological properties of the solution. And this is why we can learn more about these micelles by performing intrinsic viscosity analysis, because it will give us multiple parameters, including the size of these micelles. So to determine if we can perform the intrinsic viscosity analysis, we need to ensure that we're in that dilute regime that Soha was mentioning. And this is this is characterized by this polynomial rise in viscosity with concentration. So here we have this polynomial rise in viscosity. So that's indicating we can perform the analysis. And typically you can perform the analysis if your viscosity is around less than 1.5 to 2 centipoint. So these symbols actually have error bars, and they're smaller than the symbol, so they cannot be seen. So this is again showing that high repeatability that Soha was mentioning earlier. Now with, I'm showing it with MBROC, with Initium, where Soha was showing it earlier with MBROC2. So for each concentration, you would only need 90 microliters of sample for each test. So that's very, that's a significant advantage. So to perform the intrinsic viscosity analysis, we need to rescale the viscosity, like Soha mentioned. So I'll give you another quick description of the two equations that Soha mentioned. So if we take the viscosity of the sample, the viscosity of the solvents, and the concentration to get the two rescaled viscosities. So one is the reduced viscosity, the other is the inherent viscosity. And we can see that the rescaled viscosity, now it has this linear dependence to the concentration. So this is what Soha showed earlier as well. And then we can see that the y-intercept, this is going to be your intrinsic viscosity. So the equation with the reduced viscosity is that Huggins equation, while the one with the inherent is the Kramer equation that Soha showed. And as Soha stated, the slopes of these equations will give you these Huggins and Kramer constants. So if we take the linear fits of our rescaled viscosities and we extrapolate it to zero concentration, or basically the y-intercept, we get the intrinsic viscosity, which is around 0.2 in our case. So these units will be in inverse of concentration. So the intrinsic viscosity reported in the literature is about 0.15, 0.16. And this difference between theirs and ours may be due to the chemical composition between batches of this protein. If we compare this intrinsic viscosity to globular protein like BSA and DA water, the BSA one is about 3 times lower, so about 0.08. So we use the intrinsic viscosity values along with the reported molecular weight. Sorry, there's an issue with it. Along with the reported molecular weight to calculate the hydrodynamic radius. So basically this hydrodynamic radius is that of if you're hydrated or your solvated micelle. And this radius can also be calculated from the diffusion coefficient using the Stokes-Einstein equation that Soha mentioned earlier. If you want derivation of these equations, you can check our previous app note on intrinsic viscosity analysis of protein solutions. So that's a really nice guide for that. So in this case, we obtained the hydrodynamic radius to be 11 to 12 nanometers. And this agreed with values for micelles in dilute solution from the literature. So if we compare this to the radius of BSA protein, the BSA one is less than half at around 4 or 5 nanometers. Now, if we take the concentration, the micelle molecular weight, and the hydrodynamic radius, we can calculate the volume fraction. So the volume fraction is essentially equal to the micelle number density times the micelle hydrodynamic volume. And this micelle number density is given here by the concentration times Avogadro's constant divided by the molecular weight. And then here the hydrodynamic volume is essentially this volume for the sphere. So we do these calculations and obtain the hydrodynamic volume fraction here of 0.04 up to 0.14 in this concentration range we have here. So all of this intrinsic viscosity analysis that we've shown thus far can be performed automatically for you with the RioSense clarity analysis package. So all you have to do is import your data and concentrations, and the software will do the rest for you. So Clarity can generate a report of the results for you, and you can export your results as Excel, Word, PDF, or there are 7 other file types available. So we have recently enhanced the reprocessing capabilities of Clarity, and we have a new R-squared filter that allows you to take lower R-squared data and improve the R-squared. And it does this by taking advantage of the 4 microfluidic sensors available in the chip. So if the R-squared is a bit lower, it instead takes a combination of 3 sensors with the highest R-squared value. So because of this, you can utilize more of your data and you can have higher repeatability for your samples. So we also use the intrinsic viscosity studies to determine the reaction kinetics of polymer degradation. So in this case, we looked at guar gum, which is a polysaccharide commonly added to food products. So in particular, we looked at how guar gum in an acidic and high temperature condition degrades over time. So we did this by exposing the solution to high temperature for some time, and then we dropped the temperature to 25 to measure it. Though we could also measure at high temperature, but in this case we measured at 25. So we did this over and over again, like 40 times. So that's given here by these 40 data points. This took about 7 hours in total to complete, but it was done all automatically by the Initium with only 90 microliters of sample. And this can be done as well with Enviroc too. Also, each error bar here corresponds to the standard deviation, and they're all nearly smaller than the size of the symbols. So again, this is showing the high repeatability and accuracy of measuring these small viscosity and dilute samples. So we can see that the viscosity drops with the length of time that the sample was exposed to this higher temperature of 50 degrees. So this is indicating the sample is degrading at this condition. Now, if we increase the temperature to 70, the sample degrades even more rapidly. And this is despite both samples having the same viscosity initially. So it degrades almost down to 1 centipoint. And the viscosity here of the solvent, it was about 0.9. So we can see from the results that guar gum degradation after exposure to higher temperatures is enhanced, and there's a clear degradation for both temperatures here. So we want to further quantify this degradation of the guar gum and obtain the reaction kinetics. So to do that, we calculated the intrinsic viscosity using a different method from what we've shown in the previous slides. So here we calculated the intrinsic viscosity for each single point as the sample degraded over time. So we did this by using here the Sullivan-Ceuta equation, and you can use this equation for concentrations for which you do the same concentrations that you would have used for your other intrinsic viscosity analysis. So you can see here the equation for displayed, and this derivation for this equation can be found in the literature as well as in our previous application notes. That application note was on intrinsic viscosity analysis of polycaprolactone in chloroform solutions. So from this intrinsic viscosity, we can use the Mark-Kuvink equation that Sohai introduced to obtain the corresponding molecular weight of the guar gum over time. So this equation has those 2 parameters that Soha mentioned, the K and A. And these will depend, of course, on your polymer solvent system and other conditions like temperature, whether you added any salts or not, or excipients. So these are our values for our system. These were obtained from the literature shown there. And we can see that the molecular weight is dropping more rapidly for that sample with the greater temperature. And this is showing that enhanced degradation at that higher temperature. So to obtain the reaction kinetics, we change the molecular weight to the inverse molecular weight. And now the brown circles are corresponding to that higher temperature, whereas the teal colored, the diamonds are for that lower temperature. So the dashed lines are the fits to the data, and it's showing that there's this linear relationship between that inverse molecular rate and time. And this is especially for time after 200 minutes. So this is the case for the two temperatures, and it's suggesting that degradation is following this first order kinetics. So this is random with respect to the chain cleavage. So the rate of reaction is depending only on the concentration of the undergraded polymer chains. So this linear relationship has been previously observed and published, but in that paper in the literature, it was shown only for temperatures up to 50 degrees C by the group with Wang and colleagues. So those are, that's the review of intrinsic viscosity and some of the great things that you can do with the VROC technology to calculate it, to obtain that meaningful information for your system, like hydrodynamic radius, molecular weight. And at this point, if there's any questions, we'll be happy to take those. So the first question is, does VROC technology measure kinematic or dynamic viscosity? So the VROC technology is going to measure your dynamic viscosity. If you want to obtain the kinematic viscosity, you can refer to the, if you have the density of your sample, you can use that with your dynamic, of course, to obtain the kinematic. The next question is, what is the recommended dilution for how low you have to go to properly measure intrinsic viscosity? So the dilution, we recommend staying under about 2 centipore, 2.5 centipore. Another thing you can do is measure your sample, like under 2.5 centipore, and if that viscosity is rising quadratically with concentration, you're at the right range for your intrinsic viscosity analysis. So the next question is, how do you determine how much repeatability is necessary for a successful value? So if you're measuring, so here for the measurements I took with Initium and Soha took with MVROC 2, there's a protocol already pre-set up for you called the Intrinsic Viscosity Protocol. And this one has 10 segments.
Yes, and the key is that we run the sample at very high shear rate, which we reduce the noises of the measurement. And so running the sample at very high shear rate actually helps us to get more quality data. And as we showed, after we do rescaling, we should have a linear fit to our data. So based on that linearity, you can say if you had good measurement or not. So for example, in my case, when I showed the MVROC2 data, we saw that we have a perfect linear fit to our data, which means that we had very repeatable and high quality data.
And yes, we do have a written SOP on measuring your intrinsic viscosity. So this is a wonderful guide you can use for starting up your measurements, measuring your samples, and analyzing them afterwards. So it guides you through all the steps, all that process of getting your intrinsic viscosity analysis completed. So how is the, another question we have is, how is the intrinsic viscosity related to the dynamic and kinematic viscosity? So the intrinsic viscosity is related to the dynamic, as shown by the equations we showed in the presentation. So the Huggins and Kramer. And for kinematic, you would have to use your known fluid density to convert.
So yeah, and as we mentioned earlier, so you can also predict the viscosity of your system by having intrinsic viscosity by utilizing some models like Ross-Minton model can be used to predict the viscosity of your solution at higher concentration, I mean at a given concentration, by knowing the intrinsic viscosity. So that way you can relate intrinsic viscosity to the viscosity of your solution at for a given concentration.
And yes, you can, so there's another question here about formic acid. Yes, you can run intrinsic viscosity measurements on formic acid. Is there a difference in the results of calculating intrinsic viscosity when you do new sample load each time on MVROC 2 versus retrieval and then rerunning for repeatability? New sample.
No, actually, if you are referring to the retrieval feature of MVROC 2 or Initium, so no, actually the results should be repeatable and they should be consistent. Even after the retrieval, the viscosity measurement basically it shouldn't change. So, and what we did here and the data that we showed in this webinar, all the data were collected by using with just only one loaded sample volume. So we loaded the syringe once and then we measured it over and over. So as you saw, we had very good data and the quality of data shows that even after retrieval, your viscosity measurement is accurate.
Another question is, how would you say VROC technology is better than overloading for intrinsic viscosity? So one significant advantage of the VROC technology is with respect to dilute samples, low viscosity under 10 centipoint. And this is the range for which we're doing these intrinsic viscosity measurements. So we can measure at such high rates, get very high repeatability. And this is crucial for these intrinsic viscosity measurements. So because of that, we can get higher repeatability than these other methods available out there. Another question is, how can we consider the polydispersity of the molecules? So in this case, you're getting the an average of your hydrodynamic radius. If you're considering the polydispersity, what we've done previously is we've checked the source of chemicals we're working with to see what polydispersity is reported in their certificate of analysis. But this would be a great thing to explore with in the future with future testing.
So yeah, actually this is a very good question. Actually, the polydispersity in a polydispersed system, the polymer molecules have a range of molecular weights. So because the polymers are not solid or hard objects, and here we have a distribution of mass. So there are different radii for polymers due to this property. So yeah, that's why in the Markov equation, when we have the molecular weight, that is the average molecular weight.
Another question is, could you give more info about Kramer's coefficient and how it is related to Huggins coefficient? So these coefficients, when you add both of them, they generally will equal to 1, so 1 plus the other. There's also information in the literature on what range of particularly Huggins coefficient corresponds to different systems. And that gives you an idea of how good, whether your solvent is a good solvent or a theta solvent or a poor solvent for your flexible chains. So for example, if you have, in Soha's case, when Soha was measuring PO.
Yeah, PO in PO for the KH, I calculated was 0.37, which is perfectly aligned with the reported values in the literature. And after doing some research, I found that for KH, any value below 0.4 shows that you have a good solvent. However, if the KH or Huggins constant is greater than 0.5, shows that you have poor solvent. So in my case, since it was below 0.4, it means that I had a good solvent for my PO.
For globular, like particles, like spherical particles, that KH value can range from about 0.7 to 1.4. And that's as reported in one of the papers in the literature. So another question is, I understand higher shear rates may provide less error, but when are the random coils of spherical assumption present?
What does that mean?
And then here, the second part of that question is thermodynamic unentangled equilibrium versus reality. So the question is,
sorry, it's very long.
Yeah, it's a longer question here. So yeah, this is a longer question we have here. We can address this.
Yeah, but I think I can quickly just mention this. So for intrinsic viscosity measurements, since we are dealing with very low viscosity samples, so as you know, we have different types of chips that can handle different range of viscosities. So for this type of measurements, since we are dealing with very low viscosity, we typically use our BO5 or BO35 chips to measure the viscosity, and using these chips allows us to run the sample at higher shear rate corresponding to the highest percentage full scale of the chip, like BO5 or B035. So I just wanted to mention this because we didn't actually mention in the webinar in our talk. So typically we use our BO5 or BO35 chips for the viscosity, for the intrinsic viscosity measurements.
So here, one question is, for high molecular weight polyelectrolytes, assume tens of millions, let's say in buffered normal brine, how low of a concentration do the specific viscosity, does the relative viscosity start to deviate from linearity in those realms? Does intrinsic viscosity have any meaningful value? So I haven't tested with polyelectrolytes, but the second part of the question is, quite often at very low concentrations, the specific viscosity value increases. I see the viscosity ratio important in the range, it seems. Yeah, so I haven't tested before with polyelectrolytes. We previously did a collaboration with Carl Afton from SNP, And for those systems, we tested Polymer for enhanced oil applications. So in that case, I think the concentration we measured was under 0.1 weight percent, but I would have to check what that was. And that webinar that I mentioned right now, you can find that online for, we presented that I think a year ago. So another question is, for proteins, do you go up to really high shear rates in order to calculate intrinsic viscosity? Yes, absolutely. We would go up to, so in this case, we up to about 50,000 inverse seconds is the highest we would reach for these measurements. So the last question here is, the Markowitz equation seems to be working for chain-like molecules, polymers. How can we utilize this technique for globular proteins?
So we already have some app notes and webinar on the intrinsic viscosity of the model proteins we measured in-house, like BSA, BGG. So so I think for globular proteins, actually, the intrinsic viscosity can be measured. You still can extract information about the size of the proteins, like the hydrodynamic radius and molecular weight, by measuring intrinsic viscosity.
So another question is, for intrinsic viscosity of proteins, when you go up to 50,000, do you see 1,000 inverse seconds being not ideal? So in that case, I would definitely not see it as being ideal. I would choose that 50,000 running at 50,000 inverse seconds in the microfluidic channel, because you're going to have that higher signal to noise ratio by selecting that higher rate. And if you have these very dilute samples, they can be more difficult to measure with a rotating rheometer. So in our case, we have that advantage of the higher accuracy for these low viscosities. Okay, looks like those are all the questions. Thank you guys so much for joining the webinar. It was nice to see some familiar folks here. Thank you guys so much for the great questions, for staying during the talk, and we hope to see you again next month.
Thank you.
Thank you.